or rather, we're going to be streaming it live, in fact. So just be aware in case you are tuning in. But yeah, let's take a look at the problems, shall we? I think testing. Yeah. So unless anyone has any specific questions, I think I'll just go through them down the line. Has anybody attempted problem 1A yet? I got a different answer from what was listed there, and I'm pretty confident they made a calculation error. Has anyone taken a look at it themselves?
The teacher just came back and said that she made a calculation error as well.
Okay, all right, that sounds good. I was triple checking myself, going a little bit crazy because I thought things were very strange. But you know, I like to do these sessions slightly conversationally if students are hopefully not too shy to speak up. But for this very first problem, where we have a graph of, I guess we're calling it s of xy, or maybe just call it z, is equal to 2x squared plus 4xy. To estimate, we're using the tangent plane to estimate s of 4.2, 5.9. Does this question, I mean, I think that this is a fairly generic question, but it's kind of scary the first time you're doing these. Are you all at a comfortable place with knowing what to do, how to approach this problem? How do you feel about this one so far?
Do we do partial derivatives?
Yeah, basically. Partial derivatives is the way to go. But conceptually, I just want to know if their comfort level, if you actually understand what you're doing with these problems, because multivariable calculus, I find that a lot of students sometimes are just plugging and chugging and not really sure visually what's going on. But for a problem like this, if you have a surface, it's very hard to draw in 3D and a 2D space. But if you have a surface that kind of looks like this, and it's got a little bit of curving to it, the idea is that if you figure out the xy, and so this surface, like say this is s of xy, right, and this is at some point a comma b, the idea is that if you use this, take a tangent point, sort of take a tangent plane touching the surface at this point, you can sort of use the tangent plane to more or less estimate what the value of that surface is. It's going to be a rough estimation, but the closer it is, the more accurate it's going to be. But like, I always try to tell students to think about the one-dimensional analog for problems like these. And in your single variable calculus classes, you should have been very, very comfortable with problems where you are given a curve and you're finding a tangent plane, a tangent line to that curve at some point. And maybe in a problem like this, you'd be asked to approximate this value right here. Maybe, so if this is f of x, and this is x, and this is some point a, maybe you're asked to approximate the value of b by just sort of figuring out the equation of this line and using the line as an approximation for the point. So that's sort of, hopefully should be intuitive. We're just doing this in sort of 2 dimensions now, or I guess rather 3 dimensions. But the idea behind this problem is actually very formulaic once you do it once. But if this is our equation, z is equal to 2x squared plus 4xy, well, okay. If I remember correctly, just going off of a open textbook, the equation we have in mind is df dx at some point a comma b times x minus a plus df dy at, again, the point a b, y minus b, minus z plus f of ab is equal to 0. So, okay, maybe I'll rename it, instead of calling it f, the generic f, maybe I'll rename it to this problem and just call it s instead to make things match up nicely. But the idea here behind this problem is that they're telling you the point that they want to approximate at. Or sorry, they tell you the point that they want to approximate at, but they don't tell you the point of tangency itself. And this is one of those, I think, in my opinion, not very well written problems where you're just supposed to sort of infer that this is probably close to the values, the point 4 comma 6. Right, so this is sort of your x naught, so 4 comma 6 is going to be your a and b in this problem. It's sort of the point that, it's the point of approximation. So in the one-dimensional analog, that would be this point right here. This is the point where you're taking the tangent line of. Does that make sense? So with this in mind, we're basically going to take the partial derivative with respect to x and plug in a comma b. And we're going to take the partial derivative with respect to y, plug in a and b. And then for x minus a and y minus b, that's just going to look like 4.2 minus 4 and 5.9 minus 6. Right? This, what this is saying is basically whatever the little displacement in the x direction times the slope in the x direction plus the displacement in the y direction times the slope in the y direction, plus some initial value plus the I guess the height of the original point in question is going to take you to the height of z. Right? It's going to approximate the value of z. Hopefully that makes some intuitive sense, right? The one-dimensional analog to this would basically be dy over dx times delta x is about equal to the y that you're trying to find, right? It's sort of like saying, okay, if you're trying to figure out what this point is, and using this point as an approximation, well, you're just going to figure out what the slope is and multiply that by the displacement to sort of get an approximation. And that's exactly the idea here. So at this point, the problem is just totally computational. So ds over dx, I think, is just equal to 4x plus 4y. So then dx at, in particular, 4 comma 6 is going to be equal to, I think it just comes out to be like 40, if I'm not mistaken. Then ds dy is equal to, I think it's just 4x. So ds dx at, ds dy at 4 comma 6 is just going to be equal to 16, I believe. What else do we need to know? We need to figure out what s of a comma b is. So s at 4 comma 6 is equal to, by the way, can you all hear me? I just want to make sure I'm still connected.
We can hear you. Okay. Yes, I can.
Good. But, okay, just plugging this in, we get 4 times 4 times 6. Right, I'm just using the original equation for s of xy that they gave us. And just plugging in values. So with that in mind, once we have everything here, I think this comes out to be 128. So then excuse me. So then, yeah, at this point, you just go ahead and plug everything in. You plug in 40 over here, you plug in 16 over here, and you plug in 128 here. And then A is just 4, B is just 6. And at that point, you can just figure out what Z is supposed to be. Right? At this point, we're plugging in genuine numbers. And the very last piece of this puzzle is going to be plugging in the 4.2 for X and the 5.9 for Y. Does that make sense? Maybe I should have broken this down into 2 separate steps. Maybe I should have first broken this down into writing out the equation with the explicit values. So this is going to look like 40 of X minus 4 plus 16 of Y minus 6 plus 128 is equal to Z. And then, so this is your genuine equation of the tangent plane. And then you plug in the values you want to approximate, 4.2 for x and 5.9 for y. And that comes up with an estimate for z. So is that okay? I realize I'm spending a bit of time on this question because, I don't know, I feel like I'm being a little bit redundant. But does that all make sense so far?
Yeah, it makes sense.
Yeah, I don't know exactly what the level of comfort is, because like these problems are extremely routine for me, but maybe seeing it for your first time, it's kind of confusing. Part B is basically the exact same problem. They're just asking you to infer a little bit more than you did before. So they're basically saying estimate the value of 198 squared times 103. And the spirit of the problem is to basically say, well, okay, this is a value near 200, and this is a value near 100. So basically what we want to do is represent this as a surface, z is equal to x squared y, and take the tangent plane at 200, 100, and then approximate at 198 and 103. The steps for the problem are literally identical to the previous part, so I don't know if it's necessarily worth going through to do it again. You're just doing the exact same thing with finding, with finding ds dx, ds dy, and SAB. And then you plug in your, instead of 4.2, now it's going to be like 198, and instead of 5.9, it's going to be 103. But the big idea here is basically saying this is the slope in the x direction times the displacement in the x direction, slope in y direction times the displacement in y direction, and then you sort of have your like initial point, right? Your sort of initial height at a comma b. So this is basically saying if you start at AB and then add the change in the height from sort of climbing up the x direction or climbing up the y direction, that gets you your z, right? Tangent planes are kind of a, I think, reasonably intuitive idea. I hope. In one dimension, it's very clear how you're just sort of climbing up in one direction, but now you're sort of climbing up in two, right? It's sort of like two steps instead of one. But yeah, I think that's all I really have to say about this problem. I go through and work it out for yourself. Hopefully it shouldn't be too bad. Oh, the other thing I wanted to say is that these two problems are very nice in that they sort of, z can be very easily isolated out, but there are other situations where f of x comma y comma z is sort of like x, y, and z are all sort of implicitly defined with each other, and you can't really separate it out for z. So then the equation of the plane looks like f, x, y, z is equal to 0. Like as a very simple example, you might just have like the equation of a sphere, right? Minus 16 is equal to 0. In a situation like this, it's kind of hard to isolate out z. Or at least it's a little bit sloppy. But you can find the tangent plane just fine by using a slightly different equation. Right? And that equation, if I remember correctly, is it's not all that crazy, right? I'm just writing it out as a reminder, but it's df dx at abc times x minus a plus df dy, right? It's exactly as you would hope. abc, y minus b, plus y minus b, plus df dz, right? This is what I mean by exactly as you hope. You would x z minus c equals 0. It's exactly as you hope, meaning that it's just the slope in the z direction times the displacement in z, right? And the other thing to maybe notice is that in this situation, you don't have the s. Where did it go? you don't have the s of AB just floating around anymore, because it's kind of incorporated into some of these constants. And yeah, that's probably all I have to say about that. So far, so good. Should maybe pick up the pace. Yeah. So for problem 2, I'm not going to solve these all the way. I'm sort of going to tell you the approach. By the way, are you all still there?
Yeah.
Okay. All right. X, Y, Z. So for a problem like this, you get X, Y, and Z measured in meters. So you're sort of finding the rate of change of the voltage at the point 2, 0, 1 in the direction of 1, 1, and negative 1. So if I remember correctly, for these sort of, trying to get the change in a certain direction, you're just taking the gradient of V. And that's just going to be equal to the partial derivatives, right? Vx, Vy, and Vz. So the gradient is sort of like the multidimensional equivalent of a derivative. It's basically saying this is like a greatest hits compilation of all the individual pieces of information about the partial derivatives. And the way to find the, you would just plug in 2, 0, 1. Remember that V of x is itself a function of x, y, and z. And same for the Vy and the Vz. So then you would just plug these in. You would plug these values in, and you'd get a genuine vector for the gradient. And I think at that point, you would just dot it with the unit vector of 1, 1, negative 1. Does that sound familiar?
Yeah. Do you think you, sorry, I know you said you didn't want to do all of them through, but I
Sure.
did this and I got an answer that was different from what the professor got, and I just,
All right. I will take a crack at
wanted
it
to see
then.
where I went wrong.
So V of x is equal
Thank
to,
you.
what is this, 10x minus 3y plus yz. And this is equal to, I think this is just equal to 20, because the y terms are 0. Right, so then Vy is equal to minus 3x plus xz. And that's going to be equal to minus 6 plus 2 is minus 4, I think. Is that right? Minus 6 plus 2, yeah, minus 4. And then Vz is equal to Vz is just equal to xy, which is equal to 0. So I believe my vector at this particular point is going to look like 20, negative 4, and 0. Hopefully that's right so far. So then this direction right here, the unit vector gets converted into 1, 1, negative 1, divided by the magnitude of this vector, which I think is just square root of 3. I guess it's like 1 squared plus 1 squared plus 1 squared, which is just 3.
Wait, excuse me, I have a quick question.
Yeah,
For
what's up?
20, negative 4, and 0, what do those come from again?
That's this vector right here. I found the partial derivatives Vx, Vy, and Vz, the expressions for the partial derivatives, and I plugged in 2, 0, 1. Right, so you had 10x minus 3y plus yz is the partial derivative, and then I plugged in 2, 0, 1 for x, y, and z, and got 20.
Okay, gotcha.
Yeah. So at this point, I think all we need to do is just dot these things together. Yeah, I'm getting a slightly different answer from the professor too. I think I'm getting 16 over root 3, because you just take these two things and just dot them together. And I think this is my final answer, which is just a little bit off from what the professor had. Is this what you had, the person who was talking just earlier?
Yeah, I didn't do the part where I took the vector and then I put it over the magnitude of the vector.
Right.
Why did we do that?
That's a good question. So let me remind you what the sort of gradient is, right? The gradient is basically the direction of sorry, the gradient sort of gives the direction of the greatest change, and sort of also tells you the what do you call it? Sort of also tells you the magnitude of that change, because it's a vector, right? It has both magnitude and directional information. So with this in the now that you're trying to find that the now that you're trying to find the rate of change in the 1, 1, -1 direction, the idea is you're sort of going to dot these two pieces of information together, like I did. But like, what if they gave you 10, 1, and 10, 10, and -10 instead? Because that's the exact same direction information, but then your magnitude would be like jacked up by a factor of 10, right? Or like, what if it was 100, 100, 100? Like, in some sense, you should getting the rate of change in a certain direction should not depend on the magnitude of this vector. And that's sort of your hint that you need to normalize it. You see what I'm saying? You sort of need to isolate out the direction information by turning it into a unit vector. Does that make sense?
Yes, it does.
Yeah.
Thank you.
Okay, great. Yeah, like maybe I should have led off with a conceptual explanation, because like you can never hear it too many times. But you know, if V of XYZ, instead of a voltage, let's say it's a temperature instead, right? Like, because I think it's harder to envision what voltage is. But the classic example is temperature. Let's say in this XYZ in a room, different parts of the room are different temperatures. And the gradient is essentially this little mathematical operation that, the great mathematicians of past cooked up, that just happens to, or was contrived to give you the direction of the greatest rise in temperature, right? So if some parts of the room are cold and some parts of the room are warm, if you're just standing in a room and floating about in a room and you take the gradient and you follow that gradient, it's going to give you the direction that gets warmest fastest, so to speak. And what's more is really nice about the gradient is that you can take this information and dot it with some unit vector in any direction, and it'll tell you the rate of change in that direction. And like I was saying earlier, because 1, 1, and -1, and 100, 100, -100, kind of like they're the exact same direction, right? And all that matters should be the direction, not the magnitude. Like if I said, what's the temperature change going east? It doesn't matter whether, like, all that matters is east, right? Not like, how do you put it? With calculus, we're only concerned about local changes, right? So it doesn't really make sense to say, hey, 10 miles east or 100 miles east. We're talking about locally going east. Does that make sense? That's why we kind of want to throw away the magnitude information, at least for the direction part. Now, that being said, don't get this mixed up. The magnitude is very important for the gradients, right? Because that's just that's sort of like a real physical property of the room, like how volatile are the differences in temperature. That depends on the actual room, right? And the gradient will be really, really large if there are massive fluctuations in the room. But the magnitude information is not important for the direction you're looking in. I hope that makes sense. Anyways, I think that basically answered our next parts. So if you're being asked which direction does the voltage change most rapidly, well, that's just the information. That's exactly the gradient, right? It looks like the professor just had a different value for this. Let me double check my math.
I think the professor just updated the correct answer. So I think 16 over radical 3 is the correct one.
Okay, good. Okay, good. Thanks for clarifying. Yeah, minus 3x plus xz does appear to be. I do think I'm right. Minus 6 plus 2. Yeah. So then, this is basically your answer for part B, because this is just the gradient at that point, right? I've been saying that the gradient is the direction of the most rapid change, and that's exactly what they're asking for in part B. And then for part C, they're asking what is the maximum rate of change at this point. So that's basically just taking this vector and calculating the magnitude of it. right? And that's just the classic magnitude formula: 20 squared plus minus 4 squared plus 0 squared. That's all. Alrighty. Any questions about that one?
I have a question.
What's up?
Well, it's not really a question, but it's more just like reiteration. So
Okay.
you see that the gradient is the the fastest rate of change of the.
Yeah, it sort of carries the information about. It points in the direction of fastest change, and it also kind of tells you information about how steep that slope is.
I see.
Yeah.
Okay.
And when I say steepness of slope, using the room temperature analogy, right? Like maybe, excuse me, maybe this room only varies from like 50 degrees to 60 degrees, right? But maybe it also could vary from like 500 to 600 degrees over like some stretch of distance. The gradient sort of is going to change in scale to correspond to how rapid or how big that change is.
Mm-hmm.
Yeah. Alrighty. So, okay, if we're all set, the pendulum question. You're being asked its position after 10 seconds, assuming it starts from some initial point 403. Well, okay. I think this should just be a relatively straightforward integral. Right. So it's sort of like saying the position of t is equal to the integral of velocity of t from t is equal to 0 to 10 plus whatever the initial position is at time equals 0, which is just that thing. So this is pretty straightforward, right? You're just taking the integral of a velocity vector, the definite integral from 0 to 10, which is just taking the integral of the x, y, and z components separately. So I think that should be relatively straightforward, right? I guess I'll just give you a tiny bit more where, so if you're just plugging in this for velocity of t, right, that turns into the integral of, what does this become? 4 cosine t, 10t, and 1/2 cosine t. And then you sort of have to like evaluate each of these between 0 to 10. Or just evaluate them at the bound 0 to 10, right? And that's all you got to do. So, okay, you're being asked for its speed after 10 seconds. Well, the speed is just equal to the magnitude of the velocity. So the speed at 10 seconds means that you just plug in 10 for into the velocity and just take the magnitude. That's all there is to say. And for acceleration, well, acceleration is just the derivative of velocity. So just take the element-wise derivative of each, and that's all you got to do. Right? Acceleration of t is equal to v prime of t. What else? At what time it first reaches its maximum speed? Ah, yes. I didn't explicitly solve this one, but yeah, this one's a little bit, tiny bit more involved. So the expression for speed that we had from before is just going to be speed is equal to v of the magnitude of v of t, right? So this is a little bit nasty because it looks like vx, excuse me. These aren't meant to be partials, but this is like velocity in the x direction of t. Or, yeah, what's a better notation here? I guess it's like x prime of t, y prime of t, and z prime of t. And each of these are squared, right? And they're added up. That's just your usual magnitude formula. So you're basically being asked to take the derivative of this and optimize. And that's kind of nasty because the square root kind of sucks, right? So do you all know the trick to make this problem much easier? I mean, you can do it this way if you want, but there's a trick to get rid of the square root. Do you all know what it is? Anyone? All right. So the trick is to realize that, okay, if speed is always positive, right, it's positive because we're taking a positive square root, and also, or sorry, it's non-negative, I should say. Well, just think about it, where if speed is maximized, so is the square of speed, right? Like, if you're at your maximum speed, at some time, then this quantity of speed squared is also at its maximum. And vice versa, if speed square is maximized, then so is speed. So the trick to this problem is to, instead of looking at speed, look at speed squared. And that basically just gets rid of the square root for you. See what I did there? So then you just take ddt of both sides and set that equal to 0, and solve for the time that maximizes it. Does that make sense?
Sorry, I'm
Yeah.
having a bit of. Oh, it seems like okay. So it seems like I'm having a bit of trouble understanding like what it means to find its maximum speed.
Yeah.
So, like, if I were to like use my understanding from like the previous calculus class of finding maximum speed is when like acceleration reaches 0.
Yeah.
So
Well, hang on. That's maximum velocity, right?
maximum velocity. Okay.
Right. So velocity and speed, unfortunately, are a little bit different.
Right.
You see what I'm saying?
Speed is like the only magnitude, while velocity also carries a direction.
So in a calculus 1 class, speed, like maximum speed and maximum velocity, are like almost the exact same thing because there's only like one direction and it's just positive or negative. Unfortunately, when you're in higher dimensional space, the difference becomes pretty important, and you have to start thinking about this magnitude formula with the square root.
I see.
So just to make this a tiny bit more explicit, right? This turns into the square root of, what is this, like 16t sine squared of t plus 100 plus a quarter sine squared of t. So at this point, you can forget about, right, at this point, you're taking the derivative of speed squared, which is just what's inside here, right? You can get rid of the square root by squaring it. So at that point, you're basically just taking the derivative, and at this point, it turns into one-dimensional calculus problem in t. You see that? You're just doing when ddt of 16 sine squared t plus 100 plus 1/4 sine squared t is equal to 0. Honestly, that's not very nice. That's kind of a pain in the butt, but it's solvable. Right? You will probably start getting into a double angle formula, because what does this turn into? This turns into 32 sine t cosine t plus a half sine t cosine t is equal to 0. And you can add these up, and this turns into like 33 over 2 sine t cosine t is equal to 0. And then, well, this just disappears, right? Because it's 0. And this just turns into like 2 sine. Excuse me, this, I remember your double angle formula, right? It's 1/2. What am I doing that? 1/2 sine of 2t is equal to 0. And this is 0 whenever t is some multiple of pi, right? Some multiple of pi. No, I'm stupid. This is 2t. So it should be some half pi. It should be pi over 2 plus k pi. Right?
Okay.
Yeah. Sound good?
I think.
Yeah. Oh, and since it's asking when it first reaches its maximum speed, we'll then just take pi over 2.
Mm-hmm.
Yeah. But yeah, the recording will be up soon. Go through and watch the process and work it out yourself.
Got it. Thank you.
But yeah, the trick, I mean, you could just take the derivative of this thing, but it's kind of terrible, right? You're going to have to start, it's going to turn into like 1/2 times the square root in the denominator. It's going to be kind of awful, and then you have to use chain rule. You could do it that way, but I think it's more error prone. But this is one of the classic tricks in calculus, is to look at the square instead. Did you have any problems this semester or this quarter so far that involve this trick?
I don't believe I've seen
Okay.
this trick before. Yeah.
I see. All right, well, let's move on. Yeah, so z is equal to x plus y squared, and z is equal to sine of y, and they're asking for a parametrization of the intersection. So with these things, you're sort of, okay, let's say we're parametrizing it in terms of t, right? So at this point, we ask ourselves, okay, do we want maybe z to be t? Do we want x to be t? Or do we want y to be t? And just looking at this, this is screaming at me to choose y to be t. Y is equal to t. Because dealing with a sine t isn't too bad, right? This would turn into a sine of t. Z is equal to sine of t. But if we chose like z to be t, then y would have to be equal to arc sine of t. Right? And I would much rather deal with a sine than an arc sine. And choosing x to be t would be similarly nasty, I think. So I think just playing around with this for a couple of seconds, it should be pretty clear that choosing y to be t is definitely the way to go here. It's so much, nicer than the other options. But yeah, that just turns into z is equal to sine of t, y is equal to t, and then I guess x is just equal to sine of t minus t squared. And that's all there is to it. That's all there is to this problem. Yeah, this one, it's not maybe the most educational problem because these surfaces, it's kind of hard to visualize. But you don't always have to be able to visualize the surfaces, right? This process is reasonably mechanical, and you can just carry it through of choosing one of your variables to be t and proceeding. Yeah. Any questions? All right, so the next one is between a sphere and a paraboloid. So what this kind of looks like is that's a sphere, and your paraboloid is kind of this like bowl thing down here. So looking at it, just kind of looking at it, right? The intersection kind of ought to be a circle. So let's keep that in mind. Yeah. Hopefully that's reasonably easy to visualize. But okay, basically the idea is, well, we can either plug z in over here, but that's kind of nasty because then we're going to involve like a bunch of terms to the 4th power. Instead, why don't we just why don't we just take x squared plus y squared and like plug that in for here. So basically that's minus z is equal to x squared plus y squared. So this equation becomes z squared minus z equals 20. So z squared minus z minus 20 is equal to 0. This is simple enough. We don't even need the quadratic equation. This is z minus 5 times z plus 4 equals 0. So z is equal to either 5 or negative 4. And this is actually a little bit tricky because actually only one of these solutions is valid, right? If you look at this graph over here, the paraboloid doesn't even exist in the positive, for positive values of z. Yeah, so z is equal to 5 is just like completely, it's an extraneous solution introduced by our solving process. But z is equal to minus 4 basically describes this perfectly, right? And just looking at the equation wise, if you tried to plug in z is equal to 5 here, you would get 25 plus x squared plus y squared is equal to 20, and clearly has no real solution, right? Because 25 is already greater than 20, and x squared plus y squared have to be non-negative. So this means that 5 is no good, and z is equal to minus 4 is the only good solution. So from that point on, you can plug it into either of the two equations. Plug z is equal to minus 4 into either here or there, and either way you should get the same thing. You get that x squared plus y squared is equal to 4. And this is just screaming to use a polar parametrization, because it's a circle. So this is cosine t, y is equal to 2 sine t. Good? One of the hardest things about these parametrization puzzles is to decide whether or not you're going to be using polar, in which case it's going to look like cosine t and sine t, or if you're going to be just choosing one of these to be equal to t directly. And that just requires a little bit of playing around with it and a little bit of judgment. For this particular problem, because I don't really see any x squared plus y squared niceties, that doesn't really scream polar coordinates to me, so I took the sort of conservative approach of just plugging in t for what seems to be the easiest choice. Make sense? Any questions? So remember z is equal to minus 4? Ah, okay. All right, so then for the next part, if x squared minus y squared plus z squared is equal to 2, well, we sort of did this problem before with that traces worksheet. But if we're trying to find stuff parallel to the xz plane, that sort of means to vary the values of y. Yeah? So if this is what our coordinate system looks like, it's basically saying, okay, figure out, it's like taking a bunch of like x-rays at various different values of y and figuring out what the thing has got to look like in each plane and trying to recreate it. So what that means is typically solve for y, or maybe y squared. So that turns into y squared is equal to 2 minus z squared minus x squared, I think. Yeah? Oh no, sorry, I did that wrong. Solving for y squared gives us x squared plus z squared minus 2. So then, okay, at this point, I would just choose a couple different values for y. So I would probably just do y is equal to 0, y is equal to 1, y is equal to minus 1, y is equal to 2, and see if we can find a pattern out of this. And note that positive, negative should be symmetric because y is being squared. But okay, so let's look at y is equal to 0 first. This just means that if y is equal to 0, then x squared plus z squared is equal to 2, which is just a circle of radius root 2. Yeah, root 2. Okay, so far so good. Well, the next one, if x squared plus y squared, so if y is equal to 1, then this is just equal to 3. So this is a circle of radius root 3. And I'll draw it similarly down here, just a slightly bigger circle than the middle one. But this pattern just sort of keeps going, right? If y is equal to 2, then x squared plus z squared is equal to, I think, 6. So then it just turns into a larger and larger circle of root 6. Root 6. So what that sort of means is, if this is x and this is y and this is z, it's sort of like saying that on the xz plane you have a circle of root 2, but as you go further in each direction, either to the left or to the right, you know, the cross sections are still circular, but they keep getting bigger and bigger. Can you all picture that?
Yep.
Yeah, so I would describe this as sort of like an hourglass shape. Yeah? It's sort of like saying it gets sort of pinched when it gets towards the center, but it's sort of like, the cross sections become larger and larger circles as you get away. So yeah, that should describe things pretty well, I think. This should have been a Z. I don't know why I wrote that as a Y. Okay, so that's basically all there is to that one. And then for part B, you get a slightly different equation, y is equal to z squared minus x squared, and now it's asking us about traces parallel to the xy plane. Okay, so xy plane means isolate z. And see if we can get anything that turns into z squared is equal to y plus x squared. Okay, well now I'm just going to write like z is equal to 0, z is equal to 1, z is equal to minus 1, z is equal to 2, z is equal to minus 2. So this turns into y... oh god, my computer's getting kind of laggy. Minus x squared. And that's obviously just an upside down parabola. For z is equal to 1, that turns into y is equal to 1 minus x squared. Okay. And similarly here, it's y is equal to 4 minus x squared. Right? So it's basically the same parabola every time. It's just being shifted up and up. And the further out you go, the more and more upwards it's being shifted. And just by symmetry, it's the exact same thing, right? Yeah, because z is being squared, so whether it's positive or minus should make no difference. So this basically looks like a series of, I don't know what you call them, a series of like hills maybe? So what is this? This was x and this is y. It's kind of hard to picture, but it's like, in the xy plane, you have a parabola that just sort of touches it and goes back. But then as z gets higher, it sort of like extends further a little bit. And then symmetrically on the bottom, it kind of looks like that. So I don't know. I think that kind of looks like a saddle to me. What does it look like to you guys? I think that's basically
a Pringles chip.
A Pringles chip.
Almost, very... but not really.
Okay, I see what you're saying. Yeah, no, you've honestly got a point. It's like a Pringles chip that just sort of curves infinitely. Oh my god, I've never thought about that before. A Pringles chip is literally a saddle, isn't it?
Yeah.
Wow, I cannot actually remember the last time I've had a Pringle. But, damn. Yeah, no, that's a good one. Yeah. But, no, it kind of looks like, right, it kind of looks like... Fuck. It's so hard to draw. Especially sideways. I think we had an example like this before, but it kind of looks like a bunch of parabolas dangled from a big parabola. Oops. Right. It kind of looks like a saddle. Right. So like if I was, this is sort of oriented sideways, but like a regular horse saddle, you can kind of draw like this. Yeah. So can you just imagine taking this and like rotating it 90 degrees to get this? Yeah. Anyways, that's what that is. Make sense? Any questions? How are you all feeling about this exam? Is it confusing? Is it good? Is it bad? Honestly, this is a lot of questions to do in 15 minutes. It's you got to get fast and precise with your computations.
I think it's actually half of this on the actual exam.
Oh, okay, gotcha.
Yeah.
Yeah, like the teacher makes the practice exam twice as long as the actual exam.
Well, that's
So
good.
technically, she expects you to finish all of this in 1 hour, but like on the actual exam, it's only 30 minutes of worth of exam. So it'd probably be four questions like it is on the practice exam, but
Sure.
each part only has like half of the amount of parts in
I
it.
see. Gotcha.
So for question number 4, we might just get one graph instead of 2,
Yeah, I see.
instead of so.
Okay. So do you all think that you're all set? Do you have any other questions you want to ask?
I do have one question about this problem that we're on right now.
Yep, sure. What's up?
So we know that because we're looking at traces that are parallel to xy,
Yeah.
that we're going to be changing, we're going to be changing the z values.
Mhm.
So in part A, I understood like how we're getting these different equations.
Yeah.
However, in part B, I sort of missed how you changed the equation. Oh wait, hold on.
Yeah, okay. Like the process is really no different,
Mhm.
but we're being asked to, in part, so this is our original equation they gave us, and we're being asked to isolate, we're asked to get traces of xy, which basically means to
Mhm.
isolate z.
Right.
So that's what I do. I isolate z, or rather z squared, is equal to y plus x squared, and then I just plug in a bunch of different values for z to sort of start trying to graph them and see the pattern.
Right.
So when I plug in a value of z is equal to 0, well, okay, just plug in z is equal to 0 here, and you get 0 is equal to y plus x squared. And you just rewrite that turns into y is equal to minus x squared.
Okay.
Yeah, that's the idea.
So,
And you do that for a
yeah.
bunch of different values for z, and you kind of try to see a pattern.
Yeah, just that sort of connecting that point between, after you sub in, for example, z equals 0,
Mhm.
you rearrange the equation to represent more of an equation that is a parabola.
Yeah.
And I feel like for me to do that myself, like recognizing, oh, I can rewrite this equation that resembles the standard equation for parabolas, essentially.
Yeah, I
I
see
feel
what you
like
mean.
that part is the more challenging part.
Right. It's a little bit confusing because when you see this at a first glance, you don't necessarily think parabola because there's like two squares, right? But when you plug in a 0 here and you get 0 is equal to y plus x squared, at that point, try to remember that, okay, now you're in 2D land now. The whole point of this exercise was to talk about traces rather than 3D objects. So,
Right.
okay, if 0 is equal to y plus x squared, now this turns from college math into middle school math. And, I would say that not to be condescending, but because I ultimately think one of the biggest challenges in some of these early calculus classes is to separate out, like compartmentalize what you're learning that's actually new versus what is just a rehash from previous years that just looks really scary because it's in a new context.
Right.
Right. And, but yeah, I think, one of these things is to be quick on your feet and try to have that level of confidence and recognizing that, oh, hey, once I get rid of the point of plugging in z is equal to 0 or 1 or 2 is essentially to get rid of the z.
Right.
Right. And once you do that, you can see that, oh, wait a minute, this is just a equation of a parabola that I know and love. And from there, you're reconstructing a bunch of these. Like, when I think of traces, I like to think of, like, maybe you're getting an x-ray done at a doctor's office, and they're just taking sort of scans at various depths, right?
Right.
Each x-ray is a 2D page, and it's just being done at a different depth. And they're kind of like just hanging a bunch of these x-rays side by side to kind of mentally reconstruct the original thing, right?
Yeah.
And the other thing I should have mentioned about this problem is it is actually pretty important that this is the fact that it's z squared and not like the absolute value of z is actually really important, because that sort of is what gives the saddle the shape, and that's kind of hard to capture by the traces, right? Because that's what this z basically means. The z squared basically means is what the value of the intercept is. So this intercept is 1 and this intercept is 4. And if we were to graph the next one, the intercept would have been 9, right? With z is equal to 3. But the idea is that the intercept kind of increases faster as you go along. And that's sort of what is responsible for giving this thing its shape, right? It's no coincidence that this thing itself, like this part right here, itself looks like a parabola. And that comes from the z squared. That's the z squared. If instead, for some wacky reason, this was the absolute value of z instead, if it was like if this equation was like the absolute value of z is equal to y plus x squared, then instead of a saddle, you'd get like a really uncomfortable looking saddle. that looks kind of like that, where the parabolas are sort of being like hung off a very very straight but jagged thing.
Mm-hmm.
Right? It just looks like a really, really like creased saddle now. It no longer has any curvature. These are two straight lines.
Right. Yeah.
But yeah. I think those are the problems. Any further questions? Anything else I can help with?
Could you actually go back to 4, A and B? I kind of was lost in that section and it went a little too fast.
Okay, sure. Yeah, I guess what is there to say about them? Like I remember when I was taking this class when I was a freshman, I was really scared of the parametrization problems because they just felt something about them just felt really weird. And I no longer remember that feeling very well because now they're kind of very straightforward to me. But the idea is if you're given two equations, z is equal to x plus y squared and z is equal to sine of y, right? If you just like sort of take them both to be true simultaneously, that's essentially taking the intersection of them. And at this point, we basically want to replace one of the variables, either y, z, or x, with t, and try to see if we can rewrite all the other two independent variables as t as well. Like what this is saying is that they're not necessarily all independent. They're sort of related to each other because there's two equations to relate them. So what I say is I'm just going to take a bit of an inspired choice and say that the easiest path to do this is probably choosing y is equal to t. Because I would much rather take a sine of t rather than taking the arc sine of something else. You see what I mean? Like if I chose t to be z instead, suddenly y would have to be equal to the arc sine of z or arc sine of t, and that's terrible. It's doable, but it's terrible. But okay, if you basically just plug in t for y, okay, that's one of the equations done right there. That one's basically a freebie. Then you z is equal to sine of t because you just replace y with t. And then finally in this equation, you can solve for x to get x is equal to sine of t minus t squared. And that's all there is to it.
Okay, thank you.
Yeah. So that's an example of like I guess you'd call it normal parametrization. But then here we have in part B we sort of have a polar parametrization that was kind of hinted to us because there's all these squares floating about. But it's a very similar process. Right? We had two equations to start with. And I just said to myself, all right, the simplest in this particular situation, I'm not going to just plug in t for x, y, or z right away because it looks like I might have a chance to get a circle out of this. Right? So what I did instead was z is equal to minus x squared minus y squared. I basically subbed that in and into the first equation got z squared minus z is equal to 20. Right? Just a simple algebraic substitution. I solved this and I got z was equal to 5 or negative 4. And just by either intuition or by looking at the equation carefully, you can tell that z is equal to 5 is not a valid solution because it's sort of outside the bounds of the sphere. And this paraboloid doesn't even go onto the positive part of the z-axis, so impossible. It's actually a little bit funny to me why this pops up in the first place. It's I think it's some funny thing to do with quadratics having extraneous solutions sometimes. But okay, once you lock in the value for z is equal to negative 4, then you just plug in negative 4 into either one of these equations. Like literally both of them is fine. Sorry, you plug it in for z. And then you just get x squared plus y squared is equal to 16. Sorry, what did I say 4? No, sorry, that's 4. X squared plus y squared is equal to 4, my bad. And at that point, okay, this is just screaming us parametrizing it using the standard way for a circle. And that's all you got to do. So then your final answer would be x is equal to 2 cosine t, y is equal to 2 sine t, and z is equal to negative 4. Final answer. Sound good?
Yep, thank you.
Sure. Anything else?
Sort of to help me reiterate. So when we first solved for z and when we did the using the zero product rule, we got the extraneous solution from it. So is the way that we isolated 5 to be the extraneous solution by looking at the graph that it potentially makes?
Yeah, this is one of those subtle things where you have to check yourself every now and then if you're getting an extraneous solution. A lot of the times with quadratics, you got to double check, right?
Right.
But yeah, that's exactly right. Either look at the picture or just look at the original equation and realize that it's absurd to have z is equal to +5.
Correct, because you can't have x squared plus y squared equals a negative value.
Exactly, right. There's no real solution for that. It'd have to be imaginary.
Got it. All right, thank you.
Yeah, very good. All right, people. Well, best of luck on your exam. The session is recorded and it'll be available basically immediately.